time up to this point already talking about how electrons move, right? And we've even used examples of it in our acid-base chapter. We showed curved arrows and actually required you on an exam to show how reactions happen with curved arrows. Now, we're going to take an entire video and talk about curved arrows. And we're going to do this because they are going to be key. They're going to be central to your success. To how is organic chemistry going to become easy for you? And it's going to be with curved arrows and with understanding polarity and with understanding geometries. All right, and definitely some memorization. We're going to have to memorize some things. But this is not memorization, right? This is deep understanding. So here's how curved arrows are. With curved arrows, you have a nucleophile. Do I have my marker here? With curved arrows, you have a nucleophile and you have an electrophile, right? And you draw an arrow from the nucleophile to the electrophile. All right. And here, if this proton gets taken away, hydrogen can't have two bonds, right? So this bond's got to leave. Boom. Right? And this is the way it goes. Now, there's four main ways that we are going to see curved arrows, and these three are prominent. You're going to see these all the time, over and over and over again. This one is a bit rare. Matter of fact, it's rare enough that when we see it, it's going to surprise us. So we have to sort of know that this one exists, but it's we're just going to have to be careful about rearrangements. Okay, we don't see them often enough to be ready for them. These other three we're going to see over and over and over again. All right, so nucleophilic attack is the first one. With nucleophilic attack, we have a nucleophile, which we recognized from our last conversation, an electrophile, and we simply draw an arrow from the nucleophile to the electrophile. And there's not much more to say about that. Now, it's important, critical to appreciate that the arrow starts with the electrons and it ends with the positive center. Okay? Starts with the electrons, ends with the positive center. And then when you're done, these electrons are still there. There are the same electrons, but they're shared now instead of being transferred. All right, so this looks sort of like a Lewis acid, Lewis base question, but it ends up making a bond. Still a Lewis acid, Lewis base, I guess, in a way, huh? All right, so this more to say about the nucleophile. Sometimes you can't have a nucleophile attacking an electrophile unless these electrons get kicked off, right? Because carbon can't have 5 bonds. So sometimes the nucleophilic attack is going to require more than one curved arrow. No problem. No problem at all. Carbon can't have 5 bonds. Your eyes will get used to that. You know you have an electrophile here, right? Because you have 2 electronegative elements on here, oxygen and chlorine. So this carbon is extremely electron poor. So this is definitely electrophile. You get your eyes used to that, and it'll be just obvious when you see it, okay? So the nucleophile attacks the electrophile. These electrons have got to get kicked off, and boom, there we go. All right, another example of a nucleophilic attack. Remember that from our last conversation that a pi bond, there's electron density above and below the plane, right? So that pi bond can be thought of as an electron density. It's a nucleophile. It comes in, for example, and goes on this this sulfur trioxide, and of course sulfur is going to kick an electron pair off because sulfur can't have 7 bonds. All right, this is a reaction that we see in chapter 18, but you're prepared to appreciate it already, right? Because we're looking for nucleophilic attack, and that's all it is, nucleophilic attack. Note that only one of the carbon atoms from the pi bonds uses the pair of electrons, right? So you can only make, you're not going to make a bond. That's a good point. I had forgotten to say that. It's a good thing that note was there. I had forgotten to say it. That this is only going to make a bond with one of these carbons, of course, right? All right, the second example of electrons moving is loss of a leaving group. So here I've got a carbon. This is a tertiary carbon because it's got 3 carbon-carbon bonds. And this bromine is a good leaving group. Bromide is a good leaving group. And so it leaves. And this is an example of a leaving group, okay? And of course, we're left with a tertiary carbocation in its wake. And here's your bromide, good leaving group. And this is a stable carbocation. So this is something we'll see also. We're going to see this, I think, in this chapter. Now, sometimes you're going to be given some reaction that's really elaborate. I'm going to draw this down here. I'm going to draw this up here, okay? NO2. This has got a minus on it. Double bond. Boom. Right? Okay? And so what if you were told that this went to pretty sure this is very helpful, right? It's a little difficult to read perhaps. If you were told this went to this, you would have to say to yourself, well, what happened here? Sorry for the picture. This is a little bit ugly, but it's early in the morning. Okay, clearly the chlorine is gone, and it's gone as a chloride. So you see the minus here, and this is neutral, right? So that will answer that. Agreed? Can you see that? Now, if that's the case, then we would be left with a plus here and a negative here. So let's think, oh, well, there is no plus down here. Oh, I can see, look at these. These pi electrons went here. I can see that. There they are right there, right? Then you say, well, that's going to leave a plus right here. You go, oh, wait a second. Those, look at that. Boom, right? So you can walk your way through this. And it's really a big accounting game. It's just a big accounting game. I remember a couple summers ago, I was talking to a class, and I said something that clearly was patronizing because when I said it, there was like a collective gasp. Everybody, the whole class seemed horrified that I would say such a thing. And I'll tell you what it was. What I said was, this is what you have to be able to do here is you have to be able to count. I'm sure I said it worse than that, right? Because that doesn't sound that bad. But you have to be able to count. But I said something, it must have been worse. And I realized that after I said it that I was essentially saying organic chemistry is no more difficult than counting. And that's not, of course, true. We've got lots of abstractions here. But if you can count, I'm saying it again, right? If you can count, or if you insist on yourself counting, if you constantly count, then you are at a big advantage. A little bit of a sidetrack here, but I wanted to point out that this reaction, I'm doing this with a mouse here, this reaction is not nearly as bad as it looks. Now, we don't get this for a couple more chapters, okay? But just watch out. When you have the loss of a leaving group, then you get heterolytic cleavage, and the electron goes off. The electrons go off. You see they go off because you've got the reaction memorized, right? But after they go off, you have to do some accounting you have to do some accounting. Man, my vocabulary is just horrible today. You got to count electrons, and you got to make sure everything matches up. Okay, so loss of a leaving group is a second way that we're going to see electrons move. All right, proton transfer. We did this in chapter 3. Acid base. That's all it is. I don't think I want to say much else about this. You have an electronegative element here with a lone pair of electrons on it. You have an acid, right? Hydronium. And so you say, oh, well, this lone pair of electrons attacks a hydrogen because it's an acid, right? And these electrons are left behind. By the way, can you also see, so I have a proton transfer. This is a proton transfer right here. But can you see that this is like the follow-up reaction, just like we have with nucleophilic attack? Sometimes you have another arrow to complete the story. Okay? Now, another example is you might have water come along, because now that I've got the hydrogen on there, right, we're going to be left with that, right? So now this is an acid, and so water comes and takes that, right? So this is equilibria. You're used to equilibria. It's not a big deal. Up here I'm saying, oh, the reaction goes that way, and then I'm over here I'm saying it goes the other way. Well, of course, it goes both ways, right? So it's an equilibrium. Proton transfer. Get used to it. We're going to see it over and over again. Here's another example of proton transfer. Multiple arrows may be necessary, as we said before. Okay, warned you. This is a video that's entirely dedicated to curved arrows. So we've got a base, right? We recognize hydroxide. It comes and takes a proton, and those electrons go here, and these electrons come here. Okay, and this is a reaction that you'll have memorized at one point, but this is the explanation for it. This is how it happens. Such electron flow can also be thought as proton transfer combined with resonance, right? And where this is the resonance. All right, so we'll probe that extensively. Now I'd like to talk about the fourth kind, and that's rearrangements. Now, rearrangements, in order to appreciate rearrangements, we need to think about we need to think about hyperconjugation. Just to give a little bit of background in it. We talked about this term came up once before, but I'm gonna dwell on it for a second here. Suppose you have a methyl group and a carbocation. Can you see a carbocation here? Now, if this is sp2 hybridized, if it's sp2 hybridized, right, because it only has 3 electron groups around it, well, then where's the other p? Well, it's right here. It's empty, okay, but you have an unhybridized p orbital right there. Now, it turns out that the methyl group really has got 3 CH bonds on it, right? So one of them is here, right? You remember an sp3 hybridized orbital. It's got this other little lobe back here, which we don't talk about a whole lot. So here's an sp3 hybridized orbital right there that's making a bond with an HS, right? Well, it turns out that since that's an electron dense region, it has some overlap occasionally with this unhybridized p orbital, okay? In other words, when it gets aligned with that nicely, then these electrons stabilize that unhybridized p orbital. All right, that's called hyperconjugation. By donating electron density into the empty p orbital, we don't make a lot out of that, but it's a good explanation. It sets you up to appreciate the following. It turns out then that a methyl carbocation is not very stable because there's no right, if that were a carbon and that's a hydrogen, then in this, you don't forget, you've got like this unhybridized p orbital here that's above and below the plane, right? It's perpendicular to the screen that you're looking at right now. That's the hyperconjugation right there. Let me get rid of those now. There's none of that because you only have a hydrogen. But here you've got some of that. Well, with a secondary carbocation, you've got, like maybe if this was this, right? Got 2 of them. So both of these can be, here's my unhybridized p orbital above and below the plane, right? Both of them are stabilizing that carbocation. Get rid of that now. It's a little bit ugly. Okay, and with 3, of course, 3 is even better. So a tertiary carbocation is the most stable, and a methyl carbocation is the least stable. Tertiary carbocation means you've got lots of hyperconjugation that's possible to stabilize that carbocation. Now that we know that, it's important to appreciate. Watch, this is very cool. Now that we know that, it turns out that sometimes that overlap actually jumps over because it's hyperconjugated, right? You've got this electron density here, right? And you've got, let me go back to the same color we had, an unhybridized p orbital. Remember that? Unhybridized p orbital, 2 lobes. It was red and blue in the previous slide. It actually jumps over, okay? And when it jumps over, look at this. We go from a secondary, super interesting. We go from a secondary carbocation. Can you see this is a secondary carbocation? And this is a tertiary carbocation, which is more stable. Okay, and this is called a hydride shift, a 1,2 hydride shift. Okay, when you go from a secondary carbocation to a tertiary, then you might get a shift. So watch out for this. We'll see this a couple times. All right, but I warned you, it's not common enough that you're probably never going to be really good at it because we don't do it a lot, right? So you forget, but it shows up a few times in organic 1 and in organic 2, and you need to be aware of it. Okay, so this is a hydride shift, and you could also have a methide shift where you have, and of course it can also be, this also could be that an ethyl group, right? Any kind of R group at all. But if you have a secondary carbocation and a shift will give you a tertiary carbocation, you might get this shift. Okay, I don't think I want to say anything else about that. Those are the 4 kinds. Let me go back to the first slide then that we have in this video and say, remember now, we have 4 kinds of curved arrows that we're going to see. Nucleophilic attack, which is probably the most common. Loss of a leaving group. Sometimes these go together, right? And proton transfer, super common. We will see these over and over and over again. Memorize them, practice them, get good at them, and you will find that many of the mechanisms that we worry about become obvious and simple. In rearrangements, we have to watch out for that. I'll call your attention to it when we see it. All right. Good luck.